Hi everyone. So today we're going to continue on 4.1. So hopefully today is the last video. So if I remember correctly, the last thing we talked about on last video was these four functions that's on the screen: position function, vector x; velocity function, which is vector v; the speed function, which is just v; and acceleration function, vector a. So today let's talk about an example of it, just to show you how all this thing works out. So just like what you learned last year in BC calculus, the position vector or position function basically define where you are on the curve, while the velocity vector basically tell you which way you're going. And in this case, now we have a vector that can define precisely which way you're going in higher dimension, not just going in forward and back direction like last year. Speed is the magnitude of the velocity vector, which is the reason why standard tangent vector is so important, because standard tangent vector, technically speaking, is the velocity vector which have the correct speed. So any other tangent vector would have the correct direction for the velocity, but would not have the correct speed. That's the problem. So that's the special of the standard tangent vector, which is basically the velocity vector. They are the same thing. And the speed is the magnitude of the velocity vector. And the acceleration vector, just like what we learned last year, what you learned last year in BC calculus, the acceleration vector is basically talk about which way you get pushed, because acceleration is more relating to forces. And forces is being applied when you're being pushed or pulled. So therefore, velocity tell you which way you're going, but at the same time, the acceleration will tell you which way you get being pushed to go. Now, so give you a very simple example to illustrate what happens. So let's say we given this function. We're going to let f of t equal to, since we already did a two-dimensional function, let's do a three-dimensional one. So let's say I have this function right here. So what is this function f? This function f met from R to R3. And we're going to, actually I'm not going to define a domain for this function. I can just let it go from negative infinity to positive infinity. So let's see if we can figure out the following. So remember, in this case, f represent a curve or a path in R3. How do I know that? Because any function that met from R1 to R something else represent a curve parametrically. And the curve always exists in the range, which is in this case R3. You will see me constantly ask that questions a lot over and over again, because it is something very important that I need you to kind of understand and remember, because it helps you figure things out. So I will constantly remind you that this type of function represents a curve. And yes, some of you can probably guess what happens if you don't have a single variable vector value function, but like let's say a vector value function of a servo variable, or a real value function of servo variable. What would happen? Remember, there are four different types of functions. So we'll explain to you what those other type of functions represent, and they all represent something slightly different, which changes the way we do the derivatives. That's the reason why I constantly force you to remember and think about what they are. Okay, so let's say we try to do the following. Okay, let's say we go do A. I'm going to go ahead and ask you to find the position at t equal to, let's say t equal to pi. So how do I find the position? The position is given by the function f. So therefore, when I say ask you to find the position at t equal to pi, basically I'm asking you to do f of pi. So that would be cosine pi, sine pi, pi. And so based on what you learn in trigonometry, you should recognize that cosine pi is -1, sine pi is 0, and then pi of is just pi. So therefore, at t equal to pi, this is the position that the particle is in if we were moving along this curve, followed by this function. Next, how about I ask you to find the velocity? Okay, so that would mean I have to find f prime of pi. So let's start with f prime first. So what is f prime of t? F prime of t would be equal to negative sine t cosine t 1. And so f prime at t would basically be, so in here I guess I can say this is vector x of pi. This is now can be vector v of pi, and this is vector v of t. If you want to use vector v instead, you can. So that becomes negative sine pi cosine pi 1. So that becomes 0, negative 1, 1. So that is our position. So tell me where we are at that moment, and this tell me when. Okay, so this is when, this is where. Then what is this? This is the direction of movement. Which way I'm moving? I'm moving at 0, negative 1, 1. And I guess I can also ask C, find the speed at t equal to pi. So that would be v of pi. So that would be basically be the length of 0, negative 1, 1. And so that should not be too hard to figure out. That's radical 2. So that would be how fast we're moving. And finally, we can do D. D, I'm going to ask you to find the acceleration at t equal to pi. So let's see if we can squeeze it in, because I want to keep the entire problem on the screen. Let's see. Oh, that's the problem. All right, there you go. That should be enough room. So that will be vector a of t. That will be f double prime of t. That would actually equal to negative cosine t, negative sine t, 0. So then vector a of pi, which is equal to f double prime of pi, that would equal to negative cosine pi, negative sine pi, 0 would just come out to be negative 1, 0, 0. So this basically tells me which way we've been pushed. Okay. Now, some of the things are interesting that I want to point out about this this curve. So let's start with the first thing first. So let's think about what this curve looked like first. This is actually a very interesting curve that I definitely want all of you to know what this looked like. So this curve have a cosine t, sine t, which we already established that from a circle. But as it formed the circle, the z coordinate actually will be changing. So therefore, what does it do is it actually form this graph. So I'm going to see if I can try to draw this graph, okay? So here's my x, here's my y, here's my z. So here's how the graph look like. Let's pick a nice color. How about this one? So the graph actually looks something like this. It actually starts from so it actually kind of spiral upward and downward like this along the z-axis. And it just keep on going around in a circle. Ooh, actually, you know what? I can probably draw better than this. Yeah, let's see. Oops. Let's see if we can do better. Okay, there you go. The bottom part could go better. It's probably go like this. Yeah. Okay. Yeah, probably better. Okay. Okay. So that's how. Okay, there you go. So that's what this curve looks like. Actually, it's a spiral that going up and down. So the best way I can actually kind of help you visualize it is to think of it as like the handrail of a spiral staircase that go up and down. Okay, so that would be how it look like. So somewhere along here would probably be somewhere over here would be the point -1, 0, pi. Actually, probably be in the back, actually. Maybe, let's see. Oops. Actually, the point would probably be more to the back, so maybe somewhere over here. Yeah, maybe over here. Let's say over here. -1, 0, pi. Okay? So that would be at t equal to pi. And then the object will probably go spiral around like this. Okay. Now, something interesting I do want to point out. Number one, the first thing I want to point out is this. This curve is an example of what we call a smooth curve. So I'm going to try to define what does the word smooth mean. So what is a smooth curve? A smooth curve is this. A smooth curve is a curve where its velocity vector is never equal to the zero vector. Okay, and now why is that important and why does it mean smooth curve is the following. So if you think about this velocity vector, actually define the direction of movement, but more importantly, the velocity vector also defines speed, which means that how quickly you're moving. So when your velocity vector is actually the zero vector, that will indicate that at that moment, when your velocity vector is equal to zero vector, you are actually not moving at all because you now no longer have a direction movement nor a speed. You are actually at rest. So a smooth curve is, technically speaking, is a curve that never at rest. Now, however, one thing that's interesting that still often get confused is the following. So often get confused, so does that mean a smooth curve never turn? Because they're thinking about last year in BC calculus, where they remember that when the derivative, which is in our case velocity, equal to zero, is where the curve, where the movement can turn and move in the opposite direction. But if you think about that in this case, you know that immediately that's not true, because if you simply look at the curve that I drew on the screen, notice that this curve constantly rotating in circle, meaning it's constantly turning. But yet it is still a smooth curve because if I look at the velocity function right here, notice that the last number is always 1. Therefore, no matter what we choose for t, this number will always remain 1 and therefore can never equal to a zero vector, which is the reason why this is a smooth curve. So important to write down for yourself is that when you talk about a curve in higher dimension, like R2 and R3, it doesn't have to stop moving to turn. Okay, as a matter of fact, if a curve that never stops is called a smooth curve, and it can definitely turn all the time. Like in this case, this spiral just keep turning all the time. Okay, now another thing that's interesting that I also want to point out is the following. And you actually have later on, I don't know is it in this homework, but in later homework, you actually go prove a very important concept that you probably have learned in physics. So we're going to kind of do a little bit of it right now. So what I want you to do is if you take the velocity vector at pi and dot product the acceleration vector at pi, you will notice something interesting. So here, let's see, if I take the velocity vector at pi, dot product acceleration vector at pi, I'm basically doing a dot product between 0, -1, 1, dot product -1, 0, 0. And guess what we find? it come out to be 0. What does that mean? Well, that means the velocity vector at pi is perpendicular to the acceleration at pi. A very important concept that you probably remember learning in physics, which hopefully you now make more sense. And if not, we will definitely talk more about it in the future also. Okay, and the more interesting thing is if you look at if you take the acceleration function and the velocity function and do a dot product of them, you find out you get the same exact result. It's always equal to 0, meaning that not just this is true. As a matter of fact, what is true is the velocity vector is always perpendicular to the acceleration vector in this scenario. Now, why is that important? Because in this scenario, the object is moving in circle. Okay, so maybe I'll tell you that right now. So in physics, you probably remember learning something called orbit. When you have an object moving around in a body, a mass, and it moves in circle. And when it does that, what must be true is that the acceleration must be perpendicular to velocity. So essentially, an object that moves around in orbit is, technically speaking, constantly falling toward the center. But as it falls toward the center, it has enough forward velocity to keep it falling closer to the center. And that's how it enters an orbit. So that's one of two important things that's required when you have an object enter into orbit around another object. Yes, there's only one of two important things. So for those who have learned physics will probably know what the second important thing is, but we're not going to talk about the second important thing until later on. Remember, as I said, there is a homework question that relates to this, so I would like you to actually figure that out on your own. And if not, you can always ask me during class and we can figure it out. So the last few things I want to show you is the following. The last few things I want to show you, the next thing I want to show you is this, is a concept called arc length. So arc length is not a new concept. You actually have learned this already. So I'm just going to briefly go over it. Given a function f that maps from R to Rm. So remember, f represent. And yes, I just wrote it in the beginning of the video, but I'm going to write it again because I'm going to write as often as I can to make sure you remember this concept. A function that maps from R1 to Rm represent a curve in Rm. Let's say the domain of the function, let the domain of f be, let's say, a to b. Then its length, which is called the arc length. The reason why I call it the arc length because it's a curve, or it can be a curve, so therefore it's not a strict length, but it's actually a length of like a curve. Called the arc length can be calculated by using the following integral. And it is the same integral that you learned last year. We're going to use letter L to represent arc length, which is equal to integral from a to b, v of t dt. Now, very important to understand, this v of t is the speed function, not the velocity function. Okay? Not the velocity function. So that's why there's no arrow on top. So this is a single variable integration. You're integrating through dt. Now, one thing that's interesting about this is that this integral could be difficult to do depending on what v of t is, but notice v of t is length, so therefore it could be quite difficult to do because it might involve radical of something inside. So most likely on your next test, I would probably ask you to just simply set up this integral and then evaluate the integral using your calculator. So you learned how to do that last year in BC Calculus, so you definitely have to remember how to do that so that you can, do that correctly on your next test. All right, so give you a simple example to kind of illustrate. So let's say let f of t equal to, let's say, cosine to the third t, sine to the third t. Oops. I'm going to ask you to go and calculate the arc length of f of t over the interval from 0 to pi over 2. So to do that correctly, what you need to do is first identify v of t first. So therefore, what I need to do is find vector v of t. So vector v of t will equal to this. So derivative of cosine to the third t is 3 cosine squared t multiplied by the derivative of cosine t, which is negative sine t. And the derivative of cosine to the third t is 3 sine squared t times the derivative of sine t, which is cosine t. So what is the length function? V of t, no arrow, v of t. That will equal to square root of this thing squared plus this thing squared. So that will become 9 cosine to the fourth t sine squared t plus 9 sine to the fourth t cosine squared t. So now this actually can be simplified to something rather easy, and you can actually evaluate this integral by hand. But in this case, I'm just simply going to let you just solve the integral and then just use your calculator. So if you take integral from 0 to pi over 2, square root 9 cosine to the fourth t sine squared t plus 9 sine to the fourth t cosine squared t dt. And so now if you want, you can simply just go take out your trusty little calculator and just type that in to find the answer. Okay, so we'll do that also. So if you type into your calculator correctly, I believe your answers come out to be 9 pi over 16. Whatever that number come out to be in decimal form. So that would be the arc length. The last thing I want to show you is the following. So once again is basically the concept of that you learned last year. In this concept is called vector integration, which basically relating to the following. So if you remember what we learned here, we start with our position function, which is vector x. And then we can then define the velocity v, which is equal to basically the derivative of x. And then we can then define acceleration. Which is equal to vector v prime or vector x double prime. So therefore, I can actually go from here to here through the process of differentiation. So if I given the position function, I can actually use that to find the velocity and acceleration. So now come the interesting thing, can I actually go backward? Meaning, what if I have the acceleration vector a, which is our acceleration? Can I now try to find the velocity function based on a? So the answer is obviously yes, and you learn how to do that, which is through integral. The only problem is when I integrate, I need to figure something out. And what would that be? Is an initial velocity, v sub 0. And can I define the position also? Using that, of course I can. Vector x will equal integral of vector v of t, vector v dt, plus some initial position. So that go through this process through integration instead of differentiation. So now comes the question, how do I integrate vector a or vector v? So that is where we want to talk about vector integration. So vector integration is actually quite easy. Let's say given a function f of t, which is equal to f1 of t, f2 of t, to f sub m of t. Then we can now define the integral of f of t dt to equal to this. So it shouldn't come as a surprise how we're going to define this, because we define the derivative and the limit and the continuity the same way. Is that we just basically integrate each of the coordinate function individually and then put them all together, and that would form our integral. So therefore this would just simply equal to integral of f1 of t dt, integral of f2 of t dt, to integral of f sub m of t dt. Now, however, something interesting does happen here. And what does happen is the following. When I integrate this, I do need a constant. But not just one single constant, but rather one constant for each of the integration at its associated spot. So therefore, I can actually say the following. Is that I'm going to have to add a constant vector. C1, C2, and Cm, where C1 corresponds to integration of in F1, C2 corresponding to the integration of F2, and so on and so forth. So collectively, I can say that this integral of f of t dt will just equal to some antiderivative of f plus some constant vector integration coefficient. Constant vector of integration. All right. So make sure you understand that in this case, when I integrate, I don't get one single constant, but instead I actually get a vector constant. Now, so show you as a simple concept here. Okay, give you a very simple example, and hopefully that will be our last example for this. Suppose I have the function. Let's say I have f of t equal to, let's say, 1t. Very simple function. We're going to ask you to find the integral of f of t dt. So how will you do that? So simple. So integral f of t dt, which is equal to integral of 1 comma t dt. Okay? Which basically, what does that mean? Is that it means that I'm basically integrating 1 dt and integrating t dt. The integral and the dt go inside the vector. So what is integral 1 dt? That will be t. And what is the integral of t? That will be 1/2 t squared. And of course, I will have a c1, c2 attached to it. Now, you could also write this way. By combining the two vectors together, either way is okay. Now, then let's use it on what we know. So suppose I'm going to say, let the acceleration due to gravity be given by this. Let the acceleration due to gravity be vector a of t, which is equal to 0, 0, negative g, where g is some constant defined by the gravity. So in this case, very likely to be 9.8 meters per second, or was it 32 feet per second? Negative 32 feet per second. So what I'm going to ask you to do is, let's see if we can find the position function in this case. X of t. So therefore, if you think about it, it's actually pretty straightforward. Vector v of t, which is equal to the integral of vector a of t dt. So therefore, equal to integral of 0, 0, negative g dt. So therefore, will just simply equal to 0, 0, and the integral negative g dt is negative gt. But don't forget, we have some kind of constant. In this case, I'm going to say the constant would be vector v sub 0. Whatever that might be. And now what I'm going to do is I'm going to find the position vector x of t, which is the integral of v of t, vector v of t dt. So therefore, will be the integral of 0, 0, negative gt plus vector v sub 0 dt. So what would that come out to be? So actually pretty simple. It will come out to be the following. So integral 0, 0 will still be 0, 0. And then integral negative gt with dt would actually become negative 1/2 gt squared. Some of you might recognize that part right there. Okay. Plus vector v sub 0 is a constant, so therefore when I integrate it becomes attached with t plus some constant of integration through this integration, and I'm going to call that x sub 0. And that becomes our position function, provided we know what vector x sub 0 and v sub 0 would be. Unfortunately, time is up, so I guess I'll stop right here. So make sure, if you have any question, make sure you ask during class, okay? So we can talk about it and hopefully help you understand what's going on. All right, I'll talk to you guys later. Bye-bye.